All right. Well, we have a lot to do today, that's for sure. So we have to finish up chapter 11, although there isn't that much more to go with 11. But the most important thing is that we have to cover two problem sets. Number one, we're looking at, sorry, the chapter 11 has two problem sets. And we're going to look at the second one today as soon as we're done with the chapter. And then, of course, we have the sample final to go over. So that's a lot of work. So we're going to get that done today. And of course, as you know, today is the end of the semester. Tomorrow is the beginning of the official finals week. So yeah, so that means that I will be posting the final today. I'm pretty confident that they'll allow us to have a week for that. The last time I looked, the grades weren't due until something like in the 20s. So let's just tentatively assume that you can have a week to hand in the final. But if I find out that you need to have it back to me sooner, I'll let you know. But I'm almost positive that the grades aren't even due until later on in the month anyway. So let's just assume that they're due on a week from today at midnight, unless I tell you otherwise. All right. And if that happens, I'll send you all an email and let you know. But the last time I looked, we had more than a week to go before the final, the grades are actually due. So let's just set it at a week, and I'll make an announcement about that as well. Anyway, so in the meantime, so I got chapter 11 open here. Let's also go open up the second problem set for chapter 11, which contains all the discussion about, let's see, here it is. No, wait a minute. There we go. This is the second one. This is our discussion about probability theory. We have several probability problems as well as some combinatorics. The first one, which we've already done. Oh, that's right. These were sequences. Yes, this one we finished. Okay, that one's done. But then here we have combinations, permutations, arrangements, and probability theory itself. And then, of course, the final exam, or the sample final, is a little bit of everything from chapters 4, 5, and 11. In other words, trig, exponential logarithmic functions, and sequences and probability theory. All right, let me get that open too while we're at it. Just to take a quick peek at it. So, yes, there's 25 questions in here, fill-ins, and then, oh man, this one is long. Ooh, yes, this one is pretty long, so we'll have to really get cracking on it. Okay, but we can do it. We've got time, but we don't have time to waste. So let's get started. So you might remember that in this section, we were looking at 3 rules of probability. Basically, these are designed to let us calculate probabilities for more complex situations, typically when we have 2 or more events involved. And so we already looked at the addition rule. This is the full-blown addition rule. It enables us to calculate the probability of a union of 2 events. So here's the full version, and you might recall that, oh, here we go. Oh no, they're all done. Yours, I had to do it separately just because of the problem with the pictures. I'll take care of that this afternoon. Everybody else's are done. Yours, unfortunately, remember when it arrived, I couldn't read it. So I'll do yours this afternoon. Everybody else's should have theirs. If not, I mean, look in the grade book in Moodle and you should see the grades there. Oh, wait, Christian, yours isn't done yet. Just because, like I said, I couldn't read it. And I know you sent me the new ones, but I haven't gotten to it yet. But anyway, yes, 4, 5, and 11 is what we're doing. 4 is our discussion about, once again, 4 is our discussion about exponential and logarithmic functions. 5 is the trig functions, and then we didn't do 7. 11 is sequences, counting, which means combinatorics and probability theory. So that's it. In other words, everything that we haven't done, didn't do on the first, on the midterm. All right. Originally, there were supposed to be 2 midterms, but we just didn't have time for that. So we're going to just have this first midterm, which is 1, 2, and 3, and now we're going to have everything else on the final. All right, anyway, so yes, so we had the addition rule, which tells us how to calculate the probability of a union of two events. And we also had a special version of the addition rule, which we can use when A and B happen to be mutually exclusive. And that simplifies things a little bit because then the intersection has a probability of 0. Okay, so in other words, if you jump ahead here and look at the simplified addition rule, you'll see that it's identical to the full version, except that we're missing that intersection. We don't need it because if A and B are mutually exclusive, then the probability of A and B both happening at the same time is 0. So think of this as the simplified version, and this one as the general version. This one always works. It's just that when you have mutually exclusive events, this subtraction isn't really necessary because this probability is 0. So this is where we left off. Now we're ready for the so-called complement rule. Now, for this one, we have to basically explain what complement actually means. In this context, complement has a very specific meaning. You may have run across that word in other areas too, but here it means something very specific. It means that there are two things that must be true about events A and B. The first one is that their union equals the entire sample space. And the second is that their intersection is empty. If both of these things are true, then A and B are said to be complements. If not, of course, then they're not complements. But if they are complements, then we can use a rule in order to calculate the probability of a complement. So why don't I just briefly introduce to you what this actually means. Suppose, for example, just as a quick example, suppose that an experiment consists of choosing a card from a deck, and we define A to be the event that the card is red, and B is the event that the card is black. All right, so it's a standard problem that we might run into. We already know that in this case, the sample space is the entire deck. A and B are events because they're subsets of the entire sample space. But here's what we're interested in. What do you know about playing cards? Well, all the cards in the deck are either red or black. In fact, half of them are red and half of them are black. There are no cards that are both red and black, and no card or every card has to be one or the other. So if you look at these properties very carefully, let's see if these two events qualify as complements. All right, how can we tell? We have to look at these two properties. So I'm going to ask this question, are A and B complements? All right. Well, we must check the two conditions. All right, we have this, and the second one is right here. All right, so in this case, remember the entire sample space is the deck. So is it true? Is the union of red cards and black cards equal to the entire deck? So in other words, this formal condition is equivalent to saying, is the union of the red cards and black cards equal to the entire deck? The answer is yes. So this property works. We're good here. Let's make a little space here. Yes, so that means this condition has been met. Now down here are red and black cards. mutually exclusive. And the answer is yes. In other words, there's no card that can be both red and black. Okay. So what we've just done here is proven that A and B are complements. Okay. So that being the case, if we choose to do so, we can apply the complement rule to calculate one probability based on the other one. All right, we'll see how that works in a minute. No, combinatorics is about the science of counting. This is probability theory. Combinatorics involves arrangements, combinations, and permutations. Now here, by the way, it's just a coincidence that the number of red cards and the number of black cards is the same. That doesn't have to be true for two events to be complements. Like, let me show you an example of that. Well, first of all, here we can conclude, therefore, A and B are complements because both conditions have been satisfied. All right, now let's look at another example. Let's say that you have let's say, all right, here's one. Suppose that we have, I'm trying to think of a good example of this, a real example. All right, well, here's a good one. This should be pretty straightforward. Suppose that we know that of all the coffees that Starbucks makes, 40% are decaf. And of course, the rest are regular. So imagine the following experiment takes place. All right, I randomly pick, or a worker at Starbucks, most likely. Suppose that a bag of coffee is randomly chosen. So we'll define the event A as the coffee is decaf. B, the coffee is regular. Okay, so that raises the question, are these complements? Okay, well, we have to go through the same procedure then. And we have to prove that first, this condition is met. And so is the second one. Okay, so we need, in addition to that one, we need the second condition. Both of them must be true for them to be complements. So the first one is equivalent to saying, let's say, how should we write this in English? All right, let's do it like this. Is the union of regular and decaf coffees equal to the set of all Starbucks coffees? because that's the sample space in this case, everything they make. Yes, okay. Is any coffee both regular and decaf? No. Okay, so that means that they are mutually exclusive. And so the result of this is that yes, these two sets are complements, even though they do not both represent the same proportion of Starbucks coffees. That isn't necessary. It doesn't really matter as long as all of the coffees are accounted for and there's no overlapping between them. That's really what we're looking for. All right, so that means that A and B regular and decaf are complements of each other. All right, now let me show you a case where this is not the case. Or in other words, let me show you a case where we do not have complements. Suppose now I look at a deck of cards, and this time I choose a card, a single card. A card is chosen from a deck. So A represents spades and B represents clubs. Are A and B complements? Okay, now this is a very different situation, as you can tell, because one of the conditions is true, but one of them is not, as you'll see in a second. So we must show that. And so I'll just go grab them again. Now, the second one is actually true. Let me just jump down to that one. Are spades and clubs mutually exclusive? In other words, is it possible for a card to be both? All right, so spades and clubs mutually exclusive. Yes. Okay, so this condition has been met, but is the union of spades and clubs equal to the entire deck? No, because hearts and diamonds have been left out. Okay, so in other words, the union leaves out the hearts and diamonds. So this condition fails to be met. And so our conclusion is that A and B are not complements. All right, because they don't include the entire deck. That's really the bottom line. Yes, they're mutually exclusive, but okay, so since both conditions have not been met, we conclude that A and B, spades and clubs, are not complements. Well, sure. I mean, you're trying to demonstrate there are certain definitions that have to hold whenever you define a concept in math, there are always conditions that have to be satisfied. And so you're basically showing whether those conditions have been satisfied or not. And if it's yes, well, then we have two complements. If not, in this case, then they're not. But the reason why we need to do this is because in the cases where A and B are complements, we can use the so-called complement rule to calculate probabilities. Otherwise, we have to try something different. Okay, so yes, this is not meant to be a complicated concept, but we have to understand what it means in order to apply the rule. So I'm sure you could think of other examples of complements. Let's try a few. I'm sure you can come up with some of your own. Well, you know what? You have to be aware that I have no idea what Pokemon is. I've heard of it. I don't know what it is. So no analogies with Pokemon for me, please. Try something else, something that's not so recent. That's correct. I do not know anything about Pokemon except that it's Japanese. I mean, that's the extent of my knowledge of it. But you notice I've heard of it and I know how to pronounce it correctly, but that's as far as it goes. All right. So, oh, I know Queen. Yes, I know them. But anyway, yeah, because that's going back a ways. All right. Anyway, the white and black pieces on a chessboard are complements. Does that make sense to everyone? Yes, because all the pieces are either white or black, but none of them can be both. How about the odd and even numbers in the natural numbers? Remember, the natural numbers are the numbers 1, 2, 3, etc. So within the natural numbers, they're all either odd or even. That's all we have to choose from. Okay. Okay. So that's what we mean by complements. Anyway, with all that being said, here's a little bit of notation that we want to introduce. A with a little c next to it means a complement. So whatever A is, its complement will be written as AC. And here's the rule after all that. There's really two different equivalent versions of this rule. And let's take a look at it. Here we go. So these are the two equivalent expressions of the complement rule. And you can see how easy this is. And it makes sense because between the two of them, they have to have a total probability of 1. Okay. So in other words, like with the red and the black cards in the deck, the probability of picking either a red or a black card is 1 because all the cards are either red or black. So that's where this idea originally comes from. Yes, it's easy. It's a breeze, but we have to be able to make sure that we are using it properly by formally making sure that two events are in fact complements. Otherwise, we're just going to have the wrong answer. All right, so here's a quick example of this based on the die rolling experiment that we've been using throughout the entire chapter. Just a quick reminder, the sample space here is EE, EO, OE, and OO. And you might recall also that each of these is equally likely to occur. There's only 4 of them because we're only paying attention to evens and odds when we roll the dice. If not, if we're looking at each individual number, the sample space would actually contain 36 elements. But here it only has 4 because we're only focused on evens and odds. So let's say A is the event that the second roll is even, which means EE and OE. And down here, since the second roll is odd, that's EO and OO. So before we go any further, the question is, are A and B complements? Okay, so let me just go back and copy those conditions. And then don't worry, I'll put the definitions back real fast. I just have to copy all this good stuff. All right, so let's get these back. I'll put them up here. Ooh, wait a minute. No, because we're rolling them one die after the other. In other words, if I roll the die and I get a 3 and then I get a 4, that would be OE. But if I get a 4 followed by a 3, that would be EO. So in other words, because we're only focused on the evens and odds, we don't care about the actual numbers. It's just the sequence in which I roll the 2 die. All right, here we go. So I just want to keep all this together in one place so we can follow along. And just a quick reminder, A means that we have either all right, that should be good enough. All right, so this means we have EE and OE. And down here we have EO and OO. Let me make that a little neater there. Okay, so is it true that their union is the entire sample space? Remember, the sample space, once again, is EE, EO, OE, and then finally OO. So the union of these two sets is in fact EE, OE, EO, and OO. Even though they're not written in the exact same order, this is definitely equal to the sample space. The order in a set, don't forget with this set, the order in which I list the elements is irrelevant. These are the same sets. Okay, so that part has been satisfied, fine. Now how about this one? What's the intersection between these two sets? It's empty. There's nothing in common. So this proves that A and B are complements. Well, if that's the case, then we can say, and we'll do this just for notational purposes, why don't we rewrite B as a complement? Okay, so in other words, B equals a complement. Now, what about these probabilities? All right, well, now it's such a simple case. I mean, it's pretty clear what the probability of A and B are, but why don't we pretend that we don't know how to calculate probabilities directly from the sample space? And why don't we just go ahead and apply the rule and just confirm that it works? Well, let's see. So because we know that the events are equally likely to occur, A must have a probability of 2 out of 4, because there's 2 elements in A out of the entire sample space of 4, and B is the same. All right, so we'll move on to the next slide. All of that information has been copied for you. Remember, we're treating B as a complement. And so once again, we know we have these available to us. So we're going to challenge or check this with the rules. Is this first version of the complement rule true? Well, let's see. Is it true that 1/2 equals 1 minus half? Yes. And how about this one? Oh, yes, this one works too. So now here we had a very simple job because we already knew in advance what the probabilities were. But for a more complicated scenario, especially one where you don't actually know what the sample space is, in many cases, this is the only option that you really have for calculating these probabilities, the rules. Okay, so the rules are often the quickest way of obtaining our results, although sometimes they're not the only way. You'll see, don't worry, when we get to the sample final, we may have some cases that are more complicated and where it will be more helpful to have these rules than try to count directly from the sample space, especially if the sample space is large. Then it becomes easier, often in many cases, to use the rules just because the sample space is so large. All right, now we've saved the best for last here, the so-called multiplication rule. Now, the multiplication rule involves intersections, but it does involve a new type of probability, which we haven't really been introduced to yet. So for this one, we're going to take a bit of a detour and introduce some new concepts that we'll need to fully understand what that multiplication rule is all about. All right, so it's not that difficult, but it takes a little while to get used to it. So here's what we're going to do. First of all, this is the mystery right here, conditional probabilities. The multiplication rule as it's written is written in terms of something called conditional probabilities, which we do not yet know what those mean. And in order to understand what conditional probabilities are, we need to provide a little more background. Otherwise, it won't make any sense. But once you see what it is, you'll say, oh, this is really not that complicated, but it just takes a little time to get used to it. So we're going to start with a table, a very special kind of table. This is an example that hopefully will make sense to you. We start with what's called a joint probability table, where we take a group of data and we break it up by 2 categories. Okay, so we're assuming that there's only 2 categories of interest. So we got a group, in this case, of people, and we're classifying them according to 2 things. You'll see what they are in a second. And on the table, we'll be able to define what are called joint probabilities and marginal or unconditional probabilities. Now, this is just a lot of terminology. You basically already understand what we're about to do, but there's always terminology involved, so we have to get used to it. It's like anything else. Any discipline has a lot of vocabulary that you have to learn. All right, so here's what we're doing. We're visualizing, imagine not SUNY Purchase, but another school that has a separate business school. Now, many colleges have a business school. It's not that unusual. Purchase is a very different college because the focus is on performing arts, but it has a lot of other good stuff too. But one thing they do not have is a business school. Okay, if you want that, you go somewhere else. So let's just say this is some other branch of the SUNY system that does have a business school. And let's say it's SUNY Albany. And so what we have here is students that are studying, in this example, one of 3 majors. They're either majoring in finance, accounting, or marketing. And now what these represent, BBA means they're getting a bachelor's degree. Now, your degree is probably either BA or BS for Bachelor of Science or Bachelor of Arts. And this is different. This is a Bachelor of Business Administration. It's a specialized degree, which is just for business majors. This is a college degree, and it takes 4 years, just like any other degree, but the focus is on business. MBA stands for Master of Business Administration. Oops. This is a graduate degree, it's called. That means it comes after college. In other words, you can't get an MBA unless you already have a bachelor's degree. We call that a graduate degree, meaning it comes after the bachelor's degree. So in this school, they offer both bachelor's degrees and master's degrees. And they offer 3 majors. So all 500 students in this business school are broken up by their major and the level at which they are studying, or the degree that they're working on. And so this is how all the numbers are distributed. Now, with this information in hand, we can calculate a lot of different probabilities. So we're going to define events based on this information. We're going to simplify it by using letters. So from now on, the letter B represents, for example, that a randomly chosen student from the student body is getting a bachelor's degree. Okay, so B means getting a bachelor's degree. Okay, M, for example, means getting an MBA or a graduate degree, however you want to look at it, or a master's degree. It all means the same thing. We're going to let F mean majoring in finance. Now, I'm going to run out of space here, unfortunately. But I think you get what's going on here. All right. A will be for accounting. Okay, maybe I can squeeze this in here. Now, unfortunately, you can see with marketing starts with an M, which is already taken. So we're going to randomly assign T to marketing. Okay. Oh, maybe I can squeeze this in. So those letters will tell me what level I'm studying at and what my major is. All right, so we're keeping it simple. Well, it doesn't always work out so nicely in practice. Now, of course, if you really were in a business school, there would be several other majors probably as well. Like they're adding all these new things these days, like digital. No, what do they have now? Entrepreneurship is a big one now, and they have ones that are involved. I think they have a separate major for something called digital marketing. Maybe, in other words, online marketing, and they have all kinds of stuff that keeps coming out. All kinds of new majors are sprouting up all over the place, but these are the traditional ones. These are the ones that have been around forever. And so this is your standard business school. They're all the different majors. And so now, by the way, interestingly enough, colleges love to have business schools, and if they can manage it, law schools, because that's where a lot of the revenues come from. Any private school, they'll tell you that the majority of their revenues come from the business school because it's such a popular major. The other disciplines, maybe not so much, but law schools and business schools, that's where a lot of the money comes from for a university or a college. It's big bucks here. This is where a lot of the money comes from. And a lot of the alumni from these programs also tend to give these schools a lot of money, which is not such a big deal, not so much for state universities. That comes from the state, of course, but private schools, they survive often on the donations from their alumni. And this is where a lot of them come from. And in fact, if you go to like a purchase, the dorms, the names of the dorms, I'm not quite sure how they were chosen, but if you go to a private school, you'll notice that a lot of the dorms have family names on them. Typically, that's because money came from that person who is an alumni. Whereas a purchase, I don't know how those names were chosen. The only one I know about is Fort Awesome, which apparently was the result of a contest. I didn't get all the details, but the other ones like Outback and Way Back and Way In and out there somewhere. And, you know, does anyone know where these names came from? I think they literally just describe where the dorms are located. No, you don't know? Oh, okay. Well, I guess if you're not physically in them right now, maybe you don't remember where the names came from, but it's an interesting history. But anyway, so here's the business school. Now, here's what we want to do. We want to calculate some probabilities. So why don't we start with the concept of the joint probability? Think about this for a minute. What if the alumni magazine has decided that they're going to randomly pick somebody from the business school and put them on the cover of the magazine? So they go to the business school and they randomly pick somebody. What's the probability that they chose somebody who's getting their bachelor's degree in finance? How do you suppose you would answer that question? What would your strategy be? I want to know the probability that that person I've chosen completely at random. Excellent. 130 out of 500, right? Because 130 people fall into both categories, bachelor's degree and finance. Altogether, there's 500 students in the business school. So therefore, it makes sense that this probability is 130 out of 500, or that works out to be 26%. So based on the same logic, how about if I randomly pick somebody getting their MBA in accounting? What do you suppose that probability would be? MBA in accounting. What do you suppose that would be? Well, no, MBA is here. MBA and accounting. There you go. 35 exactly. 35 always out of 500 because that's how many students there are. All right, let's do one more. Bachelor's degree in marketing. That's it. 90 out of 500 exactly, because 90 students are getting a bachelor's degree in studying marketing. Therefore, 90 out of 500 or 18% would be my probability. So if you notice, in terms of the symbols, what we're actually defining here, let's say, and this is bachelor's degree in finance, you could write this probability as B and F. This is the joint probability of B and F. So in English, this is the bachelor's degree in finance. Okay, we call this a joint probability. You notice this is the symbol intersection, which we saw earlier, and this represents and. They're all done the same way. Now, you can see all together, there are 6 different joint probabilities that we can calculate. For example, one we didn't go to is MBA in finance. That would be this one, M and F, 45 out of 500, which is 9%. So altogether, we have 6 joint probabilities in this table. And joint simply means both are true. In other words, B and F in this first case are jointly true. And I put together a little chart here so you can see them all. If you want to go back and double check, here they are. But again, it's the same exact logic. You just literally go find the cell that corresponds to these 2 events and divide that total by 500. Now, there's other probabilities here that we could calculate. For example, what about this one? What if I want to know not the probability of somebody getting a bachelor's degree in a particular discipline, but just getting a bachelor's degree? Ooh, that's a different question altogether, isn't it? Because then I'm going to include all of these 3, and my final result is 400 out of 500. All right. Or similarly, I could do the same thing with majors. What if I want to know the probability that somebody is studying finance, regardless of the level that they're studying at? Then I would add these three, and I'd come up with 175 out of 500. All right, so in other words, these totals represent another type of probabilities. These have two special names that mean the same thing. Okay. So let me just let you catch up for a second. So you notice here, I'm not calculating a joint probability. I'm just calculating the probability of a single event, and that's coming from these totals. All right. So yes, and here again, you can see the probability B, the probability of getting a bachelor's degree is 400 out of 500. Down here, we've got the probability of majoring in accounting. All right. So there's altogether 5 of these. These have a special name, and these are called marginal or unconditional probabilities. All right. Now, do you have to memorize this? Probably not, but you should be aware of these names. These are, if you notice that since there's only one event involved, it's no longer considered to be joint. We call it either marginal or unconditional. Now, then what we can do now is calculate. By the way, I just want to mention that the way this table is structured, if you notice, if what we could actually do here, and we're going to do this in the next slide, if we really need to know the absolute number of students in each category, this is fine as far as it goes, but it might be easier for us to speed things up a little. We could actually convert these numbers into probabilities by taking every one of these numbers and dividing by 500. Okay, because like, for example, right here, if I divide that by 500, I'll get a probability of 26%. There's a 26% chance that a student that I've chosen at random is getting a bachelor's degree in finance. So what we're going to do here, I'm just going to show you what this table would look like after we've done exactly that. So these joint probability tables can either contain the raw totals or probabilities. So going forward, we'll stick with this approach because it'll make things a little bit easier for the conditional probabilities, which are kind of tricky to start with. It just saves a little bit of calculation time. So this is the same table that we had before, except, in fact, let me just copy it. Hold on one second. Just so you can see them side by side. Wait a minute, where is it? There we go. Let me just grab this one. I think I can just about squeeze them both onto this slide if I'm careful. Ooh, almost. There we go. They do fit. Okay. All right. So now it should be clear to everybody what exactly is going on here. If you take all of these numbers and divide by 500, you'll get these numbers. All right. This is just this. The reason why we're doing this is just to make the calculations a little bit simpler. That's all. All right. Now, finally, we're ready for the scary probabilities, the so-called conditional probabilities. And this is the important one because this is the one that we'll need for our multiplication rule. And after, at first you'll say, wow, what's going on here? But after you've done a few of them, you'll say, oh, there's no problem here. I get it completely. So let's think about this situation. So I'm picking somebody at random again. But this time, I'm not picking a random person from the entire student body in this business school. I'm picking somebody that is known to be getting their bachelor's degree. Does that change the probability of getting somebody with a specific major? In other words, instead of picking somebody at random from the entire student body, I've focused my attention only on the bachelor's degree students. So suppose, for example, I want to know that given that I've chosen somebody getting a bachelor's degree, what is the probability that this person that I've chosen is majoring in marketing? Ooh, that's a good question. Now, let's go back to this table for a second. If I just picked somebody from the entire student body and said, what's the probability that they're majoring in marketing? I either would have said, well, it's 110 out of 500, or just plain 0.22. But now suddenly the rules are different. I know for a fact that this person I've chosen is getting their bachelor's degree. So in fact, let me copy this slide so I can do something with it. This means that whoever I've chosen, it's not an MBA student. So that means I can, in effect, rule out all of these students. And that means, since it's somebody in this group, the probability that they're studying marketing is 90 out of 400. Or down here, you could think of that as 0.18 out of 0.80. And that, well, let me just get the calculator out. 8.18 or whatever, 90 out of 400. It makes no difference. It's either one. It's going to work up 22.5%. So in symbols, what exactly did we just do? All right, here we go. Now remember, we were told that the student is getting their bachelor's degree. Okay, so we're introducing this brand new concept. This is called a conditional probability. And this bar in the middle is pronounced, or is meant to indicate, given, or given that B is true. So all of a sudden, what's happening here is that we're being told that B is known to be true. With that information in hand, what's the probability of T? Okay, now you saw that means we're ruling out master's students or MBA students. And among the bachelor students, we know that 90 out of 400 are getting their bachelor's degree in marketing, which is equivalent of 18 out of 80, 0.18 out of 80. And if you notice that 0.18 is simply the joint probability of T and B, or T and B and T, it doesn't matter what order I write them in. And then this is the unconditional probability of B. That ratio is what I'm looking for, and that's 22.5%. That's what we mean by joint probability. Now, I want to point out one very important detail here. If we just calculated the probability of T from the original data, where we're including everybody, that would be either 110 out of 500 or just plain 0.22. They're not the same. Because something's different here. We know that this is a master's degree student, whereas with PT, we do not know that. Ooh, that was complicated. So what I'm going to do is write down here something that you must always remember. The formal definition of a conditional probability is, well, right here, well, let me just write it out in the next slide. All right, here we go. Just in general, the most general possible terms for any events A and B All right. Now, if you notice in the first case, the event that I'm given, this B, is known to be true. And the numerator is the probability of A and B. The denominator is the probability of B. Down here, I've reversed the two. The numerator is the same. It's the denominator that changes. All right, so once you get this straight, this formula, you'll never have any trouble at all calculating these probabilities. All right, so when you've got that all written down, we're going to do some examples. And after you've done 5 or 6 of these, you'll say, ah, I get it. Not a problem. All right, here we go. The probability that a randomly chosen student, same situation, same business school, is pursuing an MBA, given that he or she is majoring in accounting, is, so what you need to remember is what is being given to us. Write it out in terms of the symbols. Once this is done, you're all set, because the given part is right here. The question that they want to know is, what is the probability that they're getting their MBA? That comes first. The information that they give you comes second. In other words, after that slash sign. And that in turn tells me how to calculate this. The numerator is always the joint probability of the two. This is the one that always goes in the denominator. So this is the given event, and this is the joint event. Now, once that's in place, it's easy. because you're just reading numbers off the table. All right, so I'll give you a minute to catch up and then we'll go take a look at it. All right, so let's calculate this number from our table. So the probability M given A. Now remember, we were told that the student is majoring in accounting. So in effect, we can ignore these two columns and just focus on the accounting students. Now, with that information in place, we want to know the probability that they're getting their MBA. So the MBA in accounting is this number right here. Accounting, just plain accounting, is this number. So the ratio of those two numbers, whatever that is the probability that we're looking for. It's about 16.3%. All right. So, okay, I guess we could probably stand some more practice. All right, I'll tell you what, let me make up a new one. Before we do that, I have to go steal the table. Oops. All right, let me put this back in case you haven't finished copying it. All right, let's try a different one. First, let me sneak in this table here. Oh no, how did that happen? All right, hold on 1 minute. Wow, I've never seen that before. It's refusing to obey me. All right, let's try that again. Let me just go grab the original one.
Hey, Professor, there was a drag option the minute you copied and pasted it, actually.
Really?
Mm-hmm.
And what you mean, like that?
Oh, that's even worse.
No. It's being stubborn. I recognize this. It's like an unruly child. It really is. You have to think of technology as an unruly child. It has a mind of its own, which manifests itself at the worst possible times. Or, well, there's a lot of analogies we can draw. None of them are very flattering, let me tell you. Technology works when it wants to work. That's the way it is. All right, hold on 1 second. No, I just want to get a clean copy of the joint probability table so we can start a new example. No, not that one. I want the one with all probabilities. It's just a little simpler, that's all. No. Hold on 1 second. All right, let's see if it'll allow me to work this time. Oh my God, it actually worked. All right, so here's what we're gonna do. You know what I better do? I better make another copy of that. Just in case it decides to mess with me again. There we go. All right, so let's do one more, at least one more, maybe two more. And I think we'll have the hang of it. All right, here we go. Let's try this one. Suppose that an MBA student is chosen at random. What is the probability that he or she is majoring in finance? Okay, now the way it's written, you can convert this or translate that is what is the probability of F given M, because you know that it's an MBA student. Now, unlike the other cases, we chose randomly from the entire student body. This is known to be an MBA student. Okay, so therefore, the information you know is M. What you don't know is F. So that's the given information. This is what we're trying to find out. Now, once you have that straightened out, it's easy because you write out the formal definition. It's the joint probability of these two events in the numerator. Always the bottom is the given information. Once you've got that set up, then you literally just read the information off the table. All right, so the chart is on the next slide. Why don't we copy this formula? We'll give it a minute to save itself. There's no way I want to lose all this work. It's going to save itself whether it likes it or not. There we go. All right, so here we go. So again, let me repeat all that up here. So F and M is here. Oh wait, sorry, did I draw the wrong thing here? No, it's fine. It's fine. All right, I thought I screwed it up for a second. We know that it's an MBA student. We want to know the probability that they're majoring in finance. So the known information, oh, I see what I did. No, this is fine. This is F and M. And then M is this number right here. That's the tricky part. All right, so F given M, it's the joint probability in the numerator. That's this 9%, because that's where we intersect between M and F. And the denominator with M, which means all of the MBA students, which adds up to 20%. So therefore, we have 0.45. All right. So let's do one more. I think we could use another one, and then we'll be done. Then we can go on and define the multiplication rule at long last. Very good. All right, let's see. What else can we do here? Let's say suppose that a marketing major is chosen at random. What is the probability that he or she is getting a bachelor's degree? All right, so we have to be very, very careful with our symbols here. What do we know? We know that this student is a marketing major. Remember, that's the T. All right, so that's what we know. We want to know the probability that they're getting their bachelor's degrees. So once again, we have a joint probability in the numerator, and this known information goes in the denominator. And once we have that in place, it's just a simple matter of reading it off the table. Okay. All right, so let's copy this onto the next slide. BNT is right here, and T is right here. Okay, and that ratio is 0.8182, let's say. And I mean, I hope this makes intuitive sense, because you can see that among the marketing majors, the vast majority of them are in fact getting their bachelor's degrees. For whatever reason, less MBA students are studying marketing than bachelor's students. It just worked out that way. Now we're ready for the multiplication rule. Are you ready? Are you psyched after all that? You're probably wondering what this thing is. And when you see it, you'll realize why we had to go through all these steps. First, because it's defined in terms of conditional probabilities. Now, it turns out there's two equivalent versions of the multiplication rule. So I'll show them both to you. And you can usually use, in many cases, you can use either or, but sometimes the only information you have will determine which one you can use. So let's take a look at the first version. Ooh, now you can see if I'd shown this to you 20 minutes ago, you would have said, what is this thing? Well, you know now perfectly well what this is all about. This is the conditional probability of B given A. Which means that we know that A is true. All right, now the other version of this is very similar. And the one you'll choose will depend on what information you actually have. Although in many cases, you can use both of them. All right, are we ready? I bet we are. Oh, now I'll tell you what, let me put them both together in one slide so you can see them side by side. Let me bring this back up here. All right, this way you can tell how they're different. So the one on the bottom is the equivalent version of the one on the top. They both mean the same thing. All right. So let's look at a quick example of this. Suppose that we pick a card from a deck, one of our favorite experiments, and we do the following. We define the first A to be the event that the card is an ace, and B is the event that the card is black. So we'd like to ask ourselves the following question. What's the probability that both of these are true? In other words, what is the probability that the card is a black ace? Good question. Well, we're going to use the multiplication rule to figure this out. Now, before we do this, I just want to point out, in this particular situation, we already know what the correct answer is. I'll tell you why. Because there are two black aces in the deck. But this is good because then we can prove that the multiplication rule is working. There are two black aces. If you're not familiar with cards, that's okay. The ace of spades, ace of clubs. And since there are 52 cards in the deck, so we already know in advance what the correct answer is supposed to be, but let's use our new multiplication rule to prove this. It'll be more fun that way. And in fact, we're going to use both versions of the multiplication rule to prove it. Even more fun. Woohoo! All right, so we'll start with this approach. So what is this probability? Now, the probability of A is easy. As you can see down here, the probability of an ace is 4 out of 52 because there's 4 aces out of a 52 card deck. The first one is the tricky one. This tells me the probability of a black card given that the card is an ace. And so there are 4 aces. I'll just write A spades, A clubs, A hearts, and A diamonds. You get what I mean. These are black, and these are red. So therefore, the probability of B given A is 2 out of 4, or 1/2. So when I multiply these out, I'll get 1/2 times 1 out of 13, which we already know is true. All right, so we proved that this first version of the multiplication rule works. Good. Now, what about the second version? So for that one, let me just grab the second definition. Oh, God, that keeps, all right. So this one, the B is easy because there's 26 black cards in the deck out of 52. So we have 1/2 right here. This one is the tricky one. So of the 26 black cards, 2 are aces. And again, because it's the ace of spades and the ace of clubs. Therefore, this probability is 2 out of 26 or 1 out of 13. Ah, there you go. So we got the same answer again, 1 out of 26. No matter how we approach this, we're going to get the same result, 1 out of 26. All right, now there's one more thing we need to do here. Remember with the addition rule, we had a special, simpler version, which we were allowed to use when the events were mutually exclusive. It turns out we have a similar situation with the multiplication rule. There's a special case where we can simplify it, but it doesn't require mutually exclusive events. It requires something a little bit different, which we're going to introduce right now. And that would be events that are independent. Now, independent events are 2 events where the occurrence of one does not affect the probability of the other, and vice versa. So let me just show you a quick example. Suppose that we say that A is the event that it rains tomorrow. And that B is the event that the stock market rises tomorrow. Well, I think you'll agree that the two have nothing to do with each other. Therefore, in this kind of silly example, A and B are independent. They essentially are unrelated to each other. They have nothing to do with each other. Now, here we can tell it just by just logic. I mean, why would rain affect the stock market like that? I mean, really. But we need a more formal definition of independence. So let me show it to you real fast, and then we'll see what that does to the multiplication rule. All right, let me jump ahead here a little bit. Independence requires 2 things to be true. If one or the other is true, but not both, then they're not independent. They must both be true. And that will have a very nice impact on our multiplication rule. It'll make it a little simpler for us, but we can only use this, remember, for 2 independent events. So let's see how much simpler this becomes. Are you ready? Then, in that case, there's still 2 equivalent versions, but watch how simple they become. Ooh, that's simple. Look at that. Now you're literally just multiplying 2 probabilities to come up with this joint probability, but only when the events are independent. All right, are we ready? Now, what's left is that problem set for chapter 11, the second one, where it covers what we just did here. In other words, this is now focused exclusively on probability theory and combinatorics, and then we can dive into our sample final. Okay. So, oops, sorry. All right. Okay, so I'll tell you what, it's 9:30, just about. Why don't we have our usual morning break here, and then when we get back in about 15 minutes or so, we'll dive into chapter 11, problem set number 2, and then we'll get to look at the dreaded sample final, which, yeah, it covers a little bit of everything and has fill-ins. We can do this, don't worry. It looks like a lot, but we'll finish it. Okay, so let's knock it off for a bit. I'm sure you're worn out after all that anyway, and then we'll take it from there. Okay? So I'll see you in a little while. All right, here we go. So we'll start with this chapter 11 problem set. Now, what do we have here? We've got a sample space that consists of the deck of cards. Oh, no, this is different because we're picking the cards from the deck, and we're doing it twice. All right, so we pick a card, put it back, and choose another card, but we're only paying attention to the color. All right, so in the first case, we have A is the event that both cards are red. And in the case of B, at least one card is black. All right, so the sample space then is not, it is technically the entire deck, but we only really need to break it down into the colors. So we can have two consecutive blacks, black followed by red followed by black, and red followed by red. Now here, oh, by the way, I may not have mentioned the sample points are just the elements in the set. So the sample point, now A is defined as both cards are red. So that's really simple. And so you've got two red cards, and that's the only way that can happen. And then what about B? B is the event that at least one card is black. Okay, that means all the events except two reds. BB, BR, RB. Okay, that's it. The only thing we're leaving out is two reds because we need at least one black. Now, the probabilities are easy. Each of the elements of this sample space are equally likely. So the probability of A is very easy. It's just 1 out of 4. Okay, why? Because there's 4 elements in the entire sample space and A contains 1. For similar logic, B has a probability of 3/4. Okay, in other words, let me throw in a little explanation here. There is 1 element in A and 4 in S. All elements in S are equally likely. Okay, that's the reason why we can do this. And then here, same thing. There are 3 elements in B and 4 in S. All elements in S are equally likely. Now, the intersection. Now, we could formally use the multiplication rule here, but that isn't absolutely necessary. Probably your best bet is to simply write out the elements that make up that intersection. So if you look very carefully at A and B, you'll see that they actually have no elements in common. So since A and B have no elements in common, all you have to do is say that this probability is 0. All right, so that's what that's all about. They have nothing in common. Therefore, the probability of both of them being true must be 0. Okay, so, and then you also might want to note that, and this will help us later on, A and B are mutually exclusive. Okay, very good. Nice. Okay. And, oh God, I better save this one. All right. Now, how about this one? A union B. Now, that's a different matter altogether. If you were to actually look at these two together, remember, you're creating a new set. Let me just scroll up here. So you can see them all together in one shot. Here's A and here's B, right? So if you combine these, you'll see that the combination of the two sets basically covers every possibility. RR, BB, BR, RB. Okay. The union equals the entire sample space. I just threw that in there. That you don't need to mention that, but I just wanted you to see that. So therefore, the probability must be 4 out of 4 or 1. Okay, and again, this is because the union contains 4 elements, and S is the sample space. S contains 4 elements. Each element in S is equally likely. So it's just 1. All right. Now here's our complement rules. These are easy. Now, for example, this one equals 1 minus the probability of A, as we saw a little while ago, but A itself had a probability of 1/4, which is 3/4. Now, if you want to turn these into decimals, that's fine too. You don't have to use fractions. Obviously, fractions are a little awkward, but since they're just quarters, I think we may as well stick with fractions. So this probability is 1 minus PB equals 1. Now remember from up here, the probability of B was 3/4. Okay, so 1 minus 3/4 is 1/4. And that's it. You're done. All right, now here we have a conditional probability. I'll just write this one out. So now remember though, these are mutually exclusive events. This numerator is just 0. So it really almost doesn't matter what B is. So the final result there is just 0. And then down here, again, remember just to write out this formula. And again, the numerator will be 0. So both of these turn out to be zeros. Okay, now how about this one? Are A and B mutually exclusive? The answer is yes. There's a few different ways of expressing this. You can say, for example, you only need one. A and B has an intersection that is empty, or the probability of A and B is 0. Or if you want to explain it in terms of English, you could say that A and B have no elements in common. Any one of these will do the job. And so that's why the answer is yes. Finally, for independence, now remember there's 2 conditions for independence. Both of them have to be true. So we must demonstrate, or actually, let me start this again. right, so to demonstrate independence, we must show that both of the following are true. All right, the probability of A given B is A, and the probability of B given A is B. Is this true or not, though? Well, we're going to find out in a minute that no, it's not. For example, is this true? Well, since the probability of A given B is 0, and the probability of A is a quarter, therefore, the probability of A given B does not equal the probability of A, and this means that A and B are not independent. We don't have to bother checking the second condition. Because we already know the first one is false. Okay. Okay, so those are done. Now we get another joint probability table. So we get some more practice here. Now this is a joint probability table. All the numbers have been divided out. So these are already probabilities, which is very helpful. And so for the most part, we're just looking at numbers in the table. In a few cases, we are using a rule. All right, so let's see what's going on here. Well, first of all, let's see what we've got here. We've got 3 different sodas and 2 different types, regular and diet. And so the probability of C and R, that is regular Coke. And this one, all you have to do is look in the table where Coke and regular are intersect each other. All right. Same thing for P and D, that is Diet Dr. Pepper, 0.12. Nice. And then finally SNR, that's regular Sprite, 0.15. Now S by itself is just plain Sprite. That would be the total for all the Sprites, 0.26. R is regular. We just add up all the regular flavors to come up with 0.61. Now here we use a rule, obviously the complement rule. Very nice. And then now here we're actually using the addition rule, but here's a key detail. Let me make a note of this. The columns are mutually exclusive of each other, as are the rows. Therefore, we can use the simplified addition rule. And that means that all you have to do is add up the probability of C plus P, Coke and Dr. Pepper, which come from the 2 column totals, 0.48 plus 0.26 0.74. Okay, so I just wanted to make that very clear right here. All you have to do is use these sums because those are mutually exclusive. There's no overlapping. There's no such thing, for example, as a flavor that is both Coke and Dr. Pepper. All right. So therefore, that can't happen. Same thing here with Dr. Pepper and Sprite. Add them up. Hold on, let me just split the screen. This is the complement rule. Let's go back to the slides for a second. Where is it? Oh, wait, here it is, right here. This is what we just did. So whenever you're asked for the probability of a complement, it's equal to 1 minus the probability of A itself. So for a complement, we have 1 minus the probability of A. All right, so just remember, as soon as you see a complement like that, just remember this rule. Now, they didn't ask us to prove or determine what the complements are, but whatever it is, its probability can be calculated this way. All right, so that's where I took it from. In fact, you know what I could do? This is slide 161. Okay. Now, oh, yes. So let's get back to this. By the way, I just want to mention too that R and D are actually complements of each other because all the sodas have to either be regular or diet. So if you notice very carefully, the probability of our complement actually equals the probability of diet. And that's because regular and diet are actually complements. Because all the flavors are either regular or diet, but you can't have both. All right, so now here we're adding up Dr. Pepper and Sprite, which just by coincidence are equal to each other. All right, so here's P, Dr. Pepper, here's Sprite. Now here we go, the tricky ones. The conditional probabilities. All right, here we go. So remember the definition. Always the joint probability of the two events divided by the conditional probability. This is regular Coke in the numerator, that's 0.32. In the denominator, we have just plain Coke. And so that's equal to 2/3 or 0.667. So in these cases with the conditional probabilities, you're just really trying to make sure you apply the rules correctly, the definition, I mean. Once you've done that, the rest comes right out of the table. Okay. All right, so let's do another one just to make sure. What do we have here? We've got D given S, all right? So that means what's the probability that the soda is diet given that it's Sprite? All right, so we have, again, the intersection of the two in the numerator. The denominator is this probability. D and S diet Sprite is right here, 0.11. The total for Sprite is 0.26. And this ratio is approximately equal to 0.423. And then finally, this is the same setup. This is Dr. Pepper given that it's diet. So we have P and D. So Diet Dr. Pepper is right here, 0.12. The total for all diet flavors is 0.39. And that's 0.308. All right. So you got three of them right here, and they're all exactly the same. As soon as you see that it's a conditional probability, just make sure you set it up properly, and then the rest just falls right into place. So those are easy. Now, these are all combinatoric type problems. Let's take a look at them real quickly. Number one, an author has written 8 books and wants to display them on a shelf in his office. How many different ways or how many arrangements are possible? So as soon as you see the word arrangements, all right, just remember there are n factorial ways of arranging an object. That's the key to the whole thing. Therefore, there are 8 factorial, which if you go to your calculator, turns out to be 40,322 ways of arranging these books. That seems like a lot, but it's true. 8 books, 40,320. Ooh, that's a lot. Now, in a game of 3-card poker, how many different hands are possible using a standard deck of 52 cards? All right, so since the order of the cards does not change the value of a hand, each hand is a combination. Okay, remember, a combination is a selection of objects from a collection in which the order does not matter. All right, so if you remember the formula, NCR equals so in this case, since we have 52 cards in the deck, and each hand contains 3. So therefore, we just plug in the numbers. Oh, okay, that's fine. 3 factorial. Now, n minus r is clearly 49 factorial. Now, if you plug these into your calculator, you'll see that it turns out to be 22,100. Now, I want to remind you of a little trick I showed you, I think, to speed this up a little. 52 factorial can be written as 52 times 51 times 50 times 49 factorial, which means that this ratio simplifies to 52, 51, 50, 49 factorial. Ah, look at all that simplification we have. And 3 factorial is 6. And so I think you'll find that a lot easier to manage, but you know what? You'll get the answer any way you look at it. All right, 22,100. If you have a more advanced calculator, it may already have this NCR button on it. So check that out before you take the test. If it's in there, you might as well use it. All right. So there's one more of these, and then we can move on to the sample final. Suppose that a class of 10 students plays an investment game in which there's a prize of $100 for finishing first, $50 for finishing second, and $25 for finishing third. In how many ways can the prizes be distributed? Okay, so the distribution, each distribution of prizes. Well, all right, let's put it this way. Since the order of selection matters in the distribution of the prizes, each possible distribution is a permutation. And of course, a permutation, this is a selection from a collection of objects where the order matters. All right. So in other words, the prizes, let's say there's 10 students. If the prizes are handed out as 1, 2, 3, that's very different than 2, 1, 3, because whoever gets the first number is the winner. And then we have the second place finisher, and then the third, et cetera, et cetera. So anyway, these are permutations. Now, what I'm going to do here is write down the formula for permutations, which is only slightly, oh, I realize there's a mistake there's not a mistake, but the numbers got kind of crunched together here. Hold on one second. Let me make this as neat as possible. No, the same thing happened. There, that's better. Yes, it would help if you can actually read these. Oh, actually, sorry, these are in the wrong order. What happened? No, what's going on here? All right, that should do it. All right, you're good now. All right, wonderful. Anyway, so what's the formula for permutations? It's a little different. Okay, now here n is 10 and r is 3. All right, because there's 10 students and 3 prizes. So therefore, now you can do one of two things. You can calculate those directly in your calculator, or, so that turns out to be 720. Another possibility is to say, hey, wait a minute. If that's the case, then here I must have 10 times 9 times 8 times 7 factorial. Oh, I see. 10 times 9 times 8 is 720. So you're going to get the answer any way you look at it. All right, so that's the problem set for chapter 11. That was pretty painless, I think you'll agree. So now then we can dive into the proper sample final, which contains everything. Okay, so let's get that thing out. And let's take a look at it. All right, so for this one, I've already written in the answers. Yeah, we are a little short on time here, so I want to make sure we get through all of this. So let's just quickly run through these. The first are the short answers, of course. There are quite a few of those, as a matter of fact. So let's go through those first, and then we'll work on the problems, of which the last 3 or 4 are probability questions anyway, which we are now very comfortable with. Before we do that, I just want to get out, as far as the trig goes, what you might want to do is go back to that chapter 5 and open up and there's a couple of charts in here that could come in handy. You've got your unit circle. There's also a couple of charts in here too along the way, which I sneaked in there for basic calculations. All right, if you don't want to mess around with the unit circle, there's at least here's another one. And if you're going to use the unit circle, just don't forget that for each one, it's actually good because you've got both angles and pi, radians rather. Just always remember, within each of these ordered pairs, the first number is the cosine, and the second one is the sine. But having the unit circle means there's a lot of them that are just ready for you to read them off the circle. The only problem is it's only sine and cosine. You have to figure out the rest yourself, but you know how to do that from way, way back at the beginning. We have all the relationships between the different definitions. Let's see. Somewhere along the way, oh boy, where is it? Well, anyway, somewhere along the way, we went over the relationships between the angles, and we'll do that again here. Oh, I don't know. It's not what I'm used to. I'm used to just using the brute force approach. Where is it? Where is it? Where is it? I mean, I could do that too. Sometimes I don't feel like it. Besides, sometimes, the thing is you can't search on pictures. That's part of the problem. It won't find, like if I type in T, let's say, where's T or where's Roman numeral 3, it won't find it. All right, but anyway, so we'll see that when we get to it. So here's your exponential form. Now, this is chapter 4. These are let me go get that open too while we're at it. The exponential function, this is what it looks like. So that's all you have to do for that one. The domain of an exponential, if you're not sure, if you've forgotten, it's in here somewhere. See, now this time it might be worth using your approach. I don't know about you. I personally find that shortcuts are annoying because you have to remember them all. Yeah, and see now here, oh boy. Well, anyway, it is in here, but remember the domain means what can be substituted into an exponential function here. There's no value that could lead to division by 0 or give us an irrational number. An imaginary number. So the domain is all the reals. Now, the range is a different matter altogether. The pattern with these exponentials is that either they're entirely above the horizontal axis or entirely below. And so this term right here tells me which one it is. So like down here, I might as well throw in a little sketch here. That would be a typical exponential function if a is positive. And if a is negative, it's going to look more like this. All right, well, those are not exactly masterpieces, but you get the idea. All right, what is compound interest? This is interest on interest. Whereas simple interest is the opposite. That is interest on principal. In other words, the amount that you borrowed or lent. So remember, this is our discussion about compound interest. We use this because as an application because when you're using continuous compounding, then the interest grows or the balance grows at an exponential rate. Okay. What is the base of log x? E. So just always remember, ln simply means log base e. I don't know whose idea it was to call that ln. I had nothing to do with it. Oh, sure. As soon as everything you're seeing right here will be on Moodle. Everything that I've typed plus everything I've handwritten is all going right in there. Okay. In fact, well, now that you mentioned it, let me put the date on it. Yeah, I'll put those as, and also, by the way, as soon as we're done, I'm going to post the final 4, 5, and 11. That's it. Don't worry about the rest of it. Yeah, so no, it's complete. The final is completely written. I'm just going to stick it up there as soon as we're done. You literally could start it the minute that we're finished if you want to. So remember, you've got a week, which should be plenty of time. But you know, it's a complicated test. But yes, you'll have all this right in front of you while you're studying and while you're working on it. So you can use whatever materials you want, except obviously each other. Don't call each other and ask for the answers. That's something you're not supposed to do. But your own personal materials, your slides, the videos if you need them, all the handwritten discussion here, all the solutions, everything that's on Moodle basically is available to you. And the book, there is a book, remember? I don't know if you ever used it, but there is a book. Anyway, but a common logarithm has the base 10. That's because, again, it's because these are the two most commonly used ones. Log 10, base natural log, by far the most widely used logarithms. For some applications, you might see something different. Sometimes you see 2, for example, but pretty much the majority of the time that you're using logs, it'll either be base 10 or natural log, especially in certain disciplines like finance and economics. We see the natural log all the time because it enables us to calculate continuously compounded rates of interest. Okay, now the value of log 3(1). Now remember how this works. The reason it's 0. Now, the reason why that's happening is because, I just mentioned this, 3 to the 0 power equals 1. All right, so the two of them, essentially these two statements mean the same thing. The fact that this log is 0 indicates that 3 to the 0 power equals 1. Or in general, any log, in fact, I'll mention that here, the log with any base, the log of 1 is 0 no matter what the base is. All right, that's kind of an interesting property. Anytime you're asked for the log of 1, it doesn't even matter what the base is. That's because anything raised to the 0 power is 1. Now, this is one of those, I know we put these together somewhere in the chapter, a little helpful chart. I don't remember exactly where it is. I don't think we have time to look for it, but I can guarantee you it's in there somewhere. E to the log x equals x. Okay, so in other words, just two things you should always remember when it comes to natural logs. E to the log x equals x, log e to the x equals x. It's in the slides, but since we don't have time to go look for it, we don't have time to go on a treasure hunt, let's say, just remember these two. And in fact, that builds, I just even realized this was down here. What's the value of log e to the x? Well, guess what? It's x. So just remember these two key properties. Very helpful. Now, here's an interesting one. What is the sine of 60 degrees? Well, you know what? If I were you, I would go right into here. I would either go right to my unit circle, which if you know what you could do, you could print this out. You are able to print these PowerPoint slides. You could actually just print that one page. You see what I mean? Look how much time I'm wasting looking for it. It's extremely, oh, by the way, if you're not a PowerPoint aficionado, here's what you could do to speed it up. Go to View Slide Sorter. You see what I mean? You can see a lot of them all together in one shot. And that makes our search a lot quicker. And God, there it is. Whew. All right. So 60 just so happens to be the one that I labeled here. The sine is radical 3 over 2. It doesn't ask you to explain why. It's just, well, radical 3 over 2. It just is. That's the definition. You could draw out a right triangle and use Pythagoras' theorem to prove it, but it just wants to know the value. Now the cotangent, by the way, just in case, let's just quickly, I know we're running out of time, but just a quick little review here. This is angle theta, adjacent, hypotenuse, and opposite. Over h means opposite over hypotenuse. So those are the three basic trig functions. The rest of these are derived from these. So for example, the secant is the inverse of the cosine. The cosecant is the inverse of the sine. And the cotangent is the inverse of the tangent. So if you know this way, if you're looking, let's say you're looking for the cotangent of 90 or something, and you can't directly calculate it, you might be able to figure it out by doing one of these other ones and just changing it. Like in other words, if you know the tangent, the inverse of that is the cotangent. So the cotangent of 90. Now, it just so happens, now you can see the circle does not have cotangents, or tangents for that matter. Oh, you know what else that reminds me too? There's some identities that could also help you very much. For example, don't forget that one. Anyway, the cotangent of 90. So what you can do is you could, for example, try to calculate yourself as the cosine of 90 over the sine of 90. Now, both of those are on the unit circle. If you go to 90 degrees, that would be 0 over 1, and it's just 0. Or, in this case, the second chart that I showed you in the slides, way down here at the bottom, it's already there. Okay, cotangent 90 is 0. Also, there's some more identities in here if you need them. All right, what's the relationship between cosecant and sine? Those are inverses of each other. In fact, I Yeah, oh, okay. Well, no, I'm looking for cosecant. Okay, there it is. Cosecant of t is 1 over sine t. Okay, so they're just inverses of each other. Now, the cosine of pi over 2 radians. Now, once you see radians, you should probably go to the unit circle. You don't have to, but I think it's a good idea. So let's go back. Oh, we don't need this anymore. To our old friend, the unit circle, which, you know, it's a scary looking thing. But when you finally realize what it's for, you're almost tempted to put a copy of it in your wallet just in case you need it. You never know. Oh, for God's sake. You know what I'm going to do? I'm going to write down what slide it's on. It's, you know how it is when you look for anything. It's always the last thing that you find. It's always on the bottom of a pile. There it is. 73. Let's memorize that. 73. Okay, so we're looking for the cosine of pi over 2. So pi over 2 is 90 degrees. The first one is the cosine. It's just 0. Okay. So remember, the first term in the parentheses is the cosine. The second is the sine. So because this is pi over 2 radians, that's the same as 90 degrees. And there you go. 0. Now, the radians, now remember, the way you manipulate these is that whatever you have here, pi is 180. So remember, the basic for all of this is that pi radians is 180 degrees. Therefore, pi over 4 must be pi over 4 or 45 degrees. Okay, and then coterminal, these are the ones that have the same terminal side. In other words, what does that mean? Let's just look at a picture. So going in this direction, let's say you go to 225. If you come back around this direction, this is negative 135. Those are considered to be coterminal because they both are the same location, but they were arrived at from different directions, I guess you could call it. Okay, so they both actually represent the same thing. All right, and anyway, now, here we are back to our old friend combinatorics. What is a permutation? It's a selection of objects from a collection where the order of selection matters. And so the permutation is the one where they do not matter. All right, how many arrangements can be created from 6 objects? That would be 6 factorial, the magic word there being arrangements. Whenever you see arrangements, you think about factorial. A sample space is a set containing all possible outcomes of a random experiment. This is from 11 now. An event is a subset of the sample space. Okay. And then when can the simplified addition rule be used? When the 2 events are mutually exclusive, while the simplified multiplication rule requires them to be independent, as we just learned a few minutes ago. Okay. So yes, there's a lot going on here. What are 2 events for the requirements for events to be complements? So if you want to do this with symbols, by the way, just write They're mutually exclusive, and their union is the entire sample space. It means the same thing. And then for independence, this is easy. Let's see, where is it? It didn't quite fit. There it is. These two statements have to be true. All right. Now that was it for the fill-ins. Now we get to do actual problems. Now remember, these are restricted to chapters 4, 5, and 11. The only challenge is you might have started to forget some of what we did in 4. So you might want to refresh your memories about those. All right. So we're going to look for an exponential function that passes through these 2 points. And the real challenge here is that you're dealing with 2 points and a fairly complicated expression. So just always remember, when you see exponential function, think of f of x equals ab to the x. So what I did is I put next to each other the 2 ordered pairs. Now remember, within each ordered pair, you have x, f of x, because f of x and y mean the same thing. So for example, with 2, 8, you've got 8 equals ab to the 2nd power. For the second one, the 64 is f of x, and the exponent is here. Now, what you're going to do is rearrange them algebraically. What I did here is I rearranged each and solved directly for a, and then I set them equal to each other to solve for b. Once you know b, then you can figure out a by plugging your value for b into either of these equations. Now you can see, now this is not necessarily going to be a straightforward process. What I did here is I cross multiplied both sides to come up with 8b to the 6th equals 64b squared. And then we do a little bit more algebra. Divide out b squared from both sides. Divide out the 8, then take the 4th root of both sides, and there's your b. And then for the a, I just picked this one at random. It doesn't matter, they're both the same. They're giving us the same results. And now all we have to do is replace that b squared. The b becomes 8 to the 1/4 power. And when you go through all the steps, you'll see that a equals radical 8, or 8 to the 1/2 power. So now we know that a equals 8 to the 1/2 power. B is 8 to the 1/4 power. So therefore, we have a very interesting looking function. Okay. Remember, it's a b to the x. So yes, it's not the prettiest function you've ever seen in your life, but this is what it looks like. No, these exponentials are often not very pretty at all. All right, now for the second one, it's exactly the same procedure. You've got 1, 5, 2 comma 12. And remember, in each case, the order pair is x comma f of x. So you're going to replace f of x with this value. And this is going to go here. So you've got 5 equals ab to the first, or a equals b over 5 over b. Over here, the 12 goes here. The 2 is this exponent. 12 equals ab squared. Therefore, a equals 12 over b squared. Set them equal to each other. Okay, and then here that gives us a fairly nice result. When you go through all the algebra, you can see that b equals 12 over 5, or alternatively, you can think of this as, that's right. And from up here, I just realized, yeah, a equals 5 over b, which implies that now I replace that b with 12 fifths. I've got 5 over 12 fifths, and a equals 25 twelfths. So a is 25 twelfths. B is 12 fifths. Therefore, my function is 25 twelfths All right. And that's it. That's your function. It's a little bit less awful looking than the other one, but still pretty scary looking. All right. No, number 2, this is a future value problem. An investor deposits $50,000 into a bank for 5 years that pays a rate of 8% compounded monthly. What is the future value of the sum? So that's this formula. The future value of a sum, remember, A is the future value, P is the principal or the amount that's borrowed or lent, R is the annual rate of interest, N is the compounding frequency, and T is time in years. So based on the information we have, the principal is 50,000, which is being deposited today. T is 5 for 5 years. R is 8.08 for 8%. N is 12 because this is monthly compounding. Now we just plug in the numbers. We just have to simplify a little. 0.08 over 12 is approximately this amount. You have to be careful when you're rounding numbers like this, because remember, we're multiplying it by 50,000, which is a pretty large value. The exponent becomes 60, and so when you multiply that out on your calculator, you should end up with approximately, rounding it to dollars and cents. Oops. Yes, so if you were to actually take this 1.00667 and raise it to the 60th power, you're getting a value which is just a hair under 1.5. And then you multiply that out, of course, and you'll end up with approximately $74,493.77. That's how much money you'll have in 5 years. I just threw this in here too. You don't need this information, but I just wanted to mention that because you started with $50,000, that means you've earned $24,493.77. Okay, so just in case, this equals the future value minus the principal. Okay. Now for part B, they're asking us to do the same thing with continuous compounding. Okay, the continuously compounded formula is much simpler than this one. It's A equals PE to the RT. All right, so for continuous compounding, use A equals PE to the RT. So that's, now you notice how it's not a lot bigger. In fact, it's less than $100, but that's still $100 worth of interest that belongs to you. So if they offer you continuous compounding, you take it. All right. So if you notice, like up here, it was like 74,493. It didn't jump up very much at all, but it's still worth having. Now, this group, all you're really doing is you're replacing X with this number. So it's pretty straightforward. For example, each of the X is replaced by a 1. And so, wow, this is nice and easy. This one turns out to be 6. Man, I wish they were all like this. For part B, we're replacing the X with 3, or the X's as the case may be, and then recalculating it. And so here you've got 5 minus 5. Now this is a little tricky. The exponent is 2 times 3 plus 7, or that turns out to be 13. Wow, that's a big number. More than negative 1 billion. But that's the answer. All right, for C, just replace that X with negative 2. This one is really nice. Look what happens. It just goes to e to the 0, which is 1. I like that. And then the last one, still not too complicated. For part D, just replace the X with a 0. You end up with 5e to the minus 1 power, which is you could leave it like that. It's approximately equal to 1.83940. All right, now, here we go. Some more exponential functions. These are growth functions, actually. We've done these before, but you might recall, yes, we replaced the notation a little bit, or changed it a little. Here we start, a collector pays $1 million for a Picasso painting in 2019. If the painting grows in value by 7% per year, how much will it be worth in 2029? In other words, 10 years later. In B, 2000, a rare coin was valued at $100,000. By 2015, the coin's value had risen to 122,700. What was the annual growth rate for this coin? So while we're still using this function, we're changed the format a little bit just to reinforce the idea that we're looking at something changing over time. So the x's become t's. And also a quick reminder here, don't use the actual year for t. Use 0 for the first year. Okay, so in other words, in this Picasso case, let 2019 be 0, therefore 2029 is 10. Otherwise, you'll get the wrong answer. All right, that's very important. So the t variable is 0 and then 10. Now remember, a in this formula represents the initial value of the painting. So A is the starting value, $1 million. B is 1 plus the growth rate. So if the value grows by 7% per year, B must be 1.07, not 0.07, but 1.07. So we've now established the values of T, A, and B. T is 10 because we're looking for the value of the painting 10 years later. So, but then all you're doing is solving for 1 million times 1.07 to the 10th power, which turns out to be just a hair under $2 million. 1,967,151.36. All right, now for part B, we have a very similar situation, except it's a coin instead of a painting, but it's the same idea. It grows by the same amount every year. Okay. Oh, just a quick reminder, what was going on with B? Let's move that down here. So the growth rate, oh, this one's trickier because we're solving for B. Well, actually, we're solving for B minus 1. Okay, if B is 1 plus the growth rate, then the growth rate is B minus 1. So 2000, the first year in which we own the coin, is going to be considered year 0. 2015 is year 15 then. Initially, the coin was valued at 100,000. That's A. And T is 15. What's the value of B? Okay, well, now you notice here, we were given the future value. That is the left-hand side of this equation. All that's missing is the B. So if you plug everything in, you'll see that in 15 years, the painting will be worth this much money. It was originally worth 100,000. It grew at some rate for 15 years. So we'll divide out both sides by the 100,000, and then we'll raise both sides to the 1/15th power to solve for B. All right, so in other words, what we're seeing here is that B to the 15th raised to the 1/15th power equals B. So therefore, B turned out to be, if you plug that into your calculator, 1.01373. And that means the growth rate is not that much, but that much minus 1, which is 0.0173 or 1.373% per year. Okay. All right, logs. Everybody loves logs. Well, maybe you don't, but they're easy. They're straightforward. The key detail is to remember what these actually represent. So I've written that in each of these cases. So for part A, log base 5 of x equals 2. What is x? Well, this is coming directly from the definition of a log. That implies that 5 squared equals x. In other words, the base goes here. The right-hand side is now the exponent, and this is my variable. And once you have that, it's pretty clear that 25 is x. And so there's your answer. That's it. In a similar way, in this case, I rewrite this as 2 to the 16th equals x, which means that x is 65,536. For C, it's the same idea. This implies that 3 to the 27th equals x, or wow, 7.625 times 10 to the 12th. For this one, this implies, oh my God. I didn't even bother to write out what that was kind of a foolish question to write. I mean, 216, come on. That number is so massive, your calculator might not even be able to show it. You can leave it like this in that case. All right, I shouldn't have done that. But anyway, let's simplify these. Now remember the rules. I put some of the rules in here as we go along. It'll help you. For example, the log of x times y is the log of x plus the log of y, regardless of the base, by the way. I just want to remind you that. So this one is really the same as the log of 3x to the 7th times 3x to the 4th, or you can simply rewrite it as the log of 9x to the 11th. And you're done. That's all we need. All right. Now the second one, this is a difference. Now remember how that works. Oh, it looks like I forgot to write that in here. All right, hold on one second. The log of x over y equals the difference. Let me sneak that in here. Just as a quick reminder, so therefore, if I already have a difference, that means I can rewrite this as a ratio. Okay, so this is what I did. So that equals the ratio of log 2x to the 9th over 4x squared. And I simplified a little bit, but it ends up as log x to the 7th over 4. Anyway, for C, this is the other thing. Yeah, this is the property that I wanted you to remember. Let me put it up here. So the log of wait a minute. No, that's not right. That's better. That's much better. Yes. So just make a note to myself here. All right, hold on. And so anyway, so here we've got two things going on. We're going to take the log, we're going to convert this into a product, but, oh, that's all we need. Okay. You know what? There's another thing we could have done. I guess this will do. Oh, I see what the point of this was. Okay. In other words, we have this already. The n is already down here. We moved it up to become an exponent, and then we combine them. Okay, this is fine. Here, we have a difference and a sum. So that means log of x goes in the numerator, z cubed goes in the numerator, y to the 1/2 goes in the denominator. Okay. All right, so here we're going to do some solving. Now, our job here really, you want to look around and see if maybe there's a chance that we can create on either side an equation in terms of the same base. That makes things a lot simpler. For example, 3x to the x plus 1 equals 27. 27 happens to equal 3 cubed. And you might also recall that when the exponents, when the bases are equal, we can set the exponents equal to each other. So we'll simplify this to x plus 1 equals 3. And then we end up with x equals 2. Now, if you didn't notice that, it's not a problem because all you have to do is this. You also could have done this. And you would have wound up at the same spot. Because whenever you have the log to any base, it just ends up being x. And over here, this is the log of 3 cubed, which means it's 3. So if you didn't raise this to the third power, you would have just taken the log. In other words, the log base 3 of both sides, and you would have wound up with the same result. Now for this one, I divided both sides by 4 just to get the ball rolling. And then I took the natural log of both sides. Why did I do that? Because remember, the log of e to anything, let's call this f of x. Okay, so in other words, by taking the natural log of e to the 6x, I've reduced it to 6x equals log 32. And then I can simply divide out both sides by 6. Now, number C doesn't work. Don't worry about C. It's a complete screw up. Just ignore it. There's no real, in other words, it has no real solution. Let's put it that way. So let's go on to 7, a D rather. Let me just copy this again. Anyway, so what we're going to do here is rearrange it algebraically ever so slightly. And we end up with e to the 2x minus 5 equals log of 165 over 7. Then I can, because they both are natural logs, actually, no, what I'm getting here is the same thing. The log of e to the f of x is f of x. So we end up with just 2x minus 5 equals this constant on the right. Add 5 to both sides, divide by 2, and there's your final answer. It's a mess, but it works. All righty, let's do this. Now, the rest of these, as it turns out, well, we should be very comfortable with these because we just got through throwing a bunch of them. Yes, we did. So we're in pretty good shape, I think. So here, what's happening. We flip a coin 3 times. Now, by the way, I want to show you a graph that will help you not miss any of the coin flips. When you flip 3 times, it starts out as H or T, then it can be followed up by another H. If a T can be followed by an H or a T, then this can be followed by another H, a T, Okay. So in other words, this binary tree is there to help you make sure you don't miss any of the elements in the sample space, because if you do, you're going to get all wrong answers. Okay, so then I've written it down here. I changed the order a little bit because I think it's easier to do it this way, because here you've got all the ways in which you can have 3 heads. These are all the ways in which you can have 2 heads, 1 head, and no heads. It might make it easier to do the probabilities if you do it this way. You don't have to. Now, A was defined as at least 1 head turns up, which means you're including everything except TTT. Therefore, the probability is 7/8. B is at least 2 tails, which means all of these. And that means 4/8 or 4/8 or 1/2. Okay, what about the union? Now, here's our addition rule. We can use the addition rule, or it might be easier to just write out the elements that are in the union. But if you choose to use the addition rule, you need to also calculate the probability of this intersection, which is 3/8. Okay, so when you plug in the numbers, you end up with 1, or just write out all the elements that are in P A union B, which actually turns out to be the entire sample space. And that implies that the probability must be 8/8, which is 1. Okay, either way is fine. All right, that's up to you. Okay. A intersect B, well, we already saw that. Where they are overlap. In fact, why don't we do this? This is A, and this is B. So the intersection between them is, so what do they have in common? These 3 right here. And that implies that the probability is 3/8, because there's 3 elements in the set and the entire sample space has 8. And they're all equally likely, of course. Now for A complement, you can do one of 2 things. You can either write out A complement, or else you can use the rule. So we already know that the probability of A is 7/8. See how easy that was? Now here for B, we can do the same thing. The probability of B complement is 1 minus 4/8, which is 4/8, or 1/2, of course. because we can use the rule, or else we can simply write out all the elements that belong to the complement and calculate how many there are. Then we have two conditional probabilities. And the logic is exactly the same as we had before. So remember before we said that the probability of A intersect B is 3/8 and B was 4/8. So that ratio is 3/4. So it's not zero like we did in our other problem set. And here with B given A, we have again the same intersection in the numerator, 3/8, which we saw up here somewhere. And then in the denominator we have A, whose probability was 7 out of 8. And so that reduces to 3/7. Okay. Now, are A and B mutually exclusive? No, because we've already seen that the probability of their intersection was 3/8. So therefore, they're not mutually exclusive. And of course, you can, do it in other ways too. You can point out that they have elements in common, or else you can point out that their intersection is not empty. The question about independence. Now, remember what it requires to be independent. So just a quick reminder. But you can see I've already set it up for you. Both of these are false. Okay, so both conditions, it doesn't matter if both are false or not. It just means one of them is false. That's all that matters. Since both are false, A and B are not independent. Okay, because these two conditional probabilities, this first one, 3/4 does not equal A, which remember was equal to 7/8. And for B, this conditional probability is 3/7, which does not equal B, which is 4/8. So therefore, they're not independent. Now, this time we're also being asked to calculate whether or not A and B are complements. So remember, there's two things we need for complements, or two events to be complements. And there they are right there. A unit B must equal S. A intersect B must be empty. So we saw earlier that A unit B is the entire sample space, but A intersect B is not empty. Therefore, A and B are not complements. One of the conditions holds, but not both, and that's what we need. All right, here we go, a joint probability table. We love joint probability tables. So for example, now this one is coffee, as you can see, French roast, Guatemala, and espresso, decaf and regular. So these first two, we can read straight off the table. I've got them down here. F and D is 0.18. Oh boy, hold on. Let me find my place. Okay, good. So R and D, which is regular espresso, is just 0.28. Oh, sorry, I looked at the wrong one. That's French roast, sorry. Regular espresso is 0.10 right here. F is French roast, that has a total of 46, 0.46. Regular is this row total of 0.50. D complement, there it is again. We're using the complement rule. D has a probability of 0.5. Therefore, its complement has a probability of 1 minus that, which is also, by coincidence, equal to 0.5. Now, for F or G, French roast or Guatemala, if you notice, I've written out the full addition rule here. This piece is not necessary because it's just equal to 0. So you can leave it out or just throw it in here. Either way, you'll get a total of 0.46 plus 0.22, which is 0.68. G or E, Guatemala or espresso, is 0.54. Now, these are the two conditional probabilities. D given F is D and F over F. Okay, D and F is decaf French roast or 0.18. F down here is French roast, 0.46. And that leaves me with 0.3913. And then finally, R given E. That's regular espresso over espresso, or regular espresso is here, 0.10, and espresso is 0.32. That ratio is 0.3125. So we like this table. It's really straightforward. All right, now this last problem is combinatorics, just like we had before. First, we have license plates that contain 5 letters that are randomly chosen from the alphabet with no repeats. How many different plates are possible? That's part A. Well, clearly, each plate is a permutation since the order of selection matters. I'm choosing 5 objects from 26 because I'm choosing 5 letters from the alphabet. So if you use the NPR formula, n factorial is divided by n minus r factorial. So I have 26 factorial over 26 minus 5 factorial, 26 factorial over 21 factorial, which finally ends up being 7 million. Wow, 893,600. That's a lot of plates. But, of course, in the real world, that's probably not enough. That's why they have letters and numbers, and there's usually at least 6 digits. But anyway, how about B? What's going on with B? A bakery offers a new style of layer cake. The customers may choose any 3 flavors from 6. How many choices do they have? Well, here, the order in which I select my layer cakes is completely irrelevant. Therefore, these are combinations. I'm choosing 3 layers out of 6 or 3 flavors out of 6. So remember, the NCR formula is a little messier. It's n factorial over n minus r factorial times r factorial. So when I plug in these numbers, now these aren't so large that you need to reduce them. You've actually got 720 over 6 times 6, or 720 over 36, which is 20. Okay. Now, if you happen to own the calculator with this function, you're in good shape. You can just plug in those numbers and you'll get 20. If not, you can use it with the formula. And then finally, we have a bookshelf with 3 titles, as you can see. How many different ways can we arrange them? And again, the minute you see the word range, you think about factorial. So therefore, there must be 3 factorial ways, or 6 ways of arranging the 3 books. Wow, that's it. Now, since these last 3 are exactly what we did earlier, they should be very familiar to you. Some of these you might have started to forget. But basically, this is it in a nutshell. So I think we're done. So I'm gonna need to post everything we did today plus the final exam. So you should send it back to me by this time next Wednesday, or actually by midnight next Wednesday. All right, and then you'll be all set. And then maybe you have calculus to look forward to in the fall. I don't know. Or maybe this is sadly the end of your math career. I don't know. I hope it's not. But if it is, I hope you'll learn something useful here. You'll have a lot more math skills than the average person you'll meet outside of the math majors, of course. And that's only going to help you because everything in the future will ultimately come down to math. I think you'll agree as we become a more technological society. So all of this is good. May not seem like it now, but yes, it's all going to help you in the future. All right, so if you don't have any last minute questions, I guess we'll have to stop right here. And now, of course, you can always send me questions by email if you get stuck on one of the questions or it's not clear what it means or something like that happens. That's okay. You can just let me know and I'll get back to you and let you know what's going on. But I think you'll find that the actual final is pretty much exactly what you're seeing here. No, we don't have any extra credit, but your job, if you can just really crank it up and really do your best possible job in the final, that should be tremendously helpful. All right, any other questions? All right, well, it's been fun. I can't say that I'll see you again in the future, but you never know. I mean, it's possible. So, and I hope everything works out for you and have fun with your majors and have a good life, I guess. All right, you're welcome, everyone.
Thank you, Professor.
That's right. Yes, everything's based on the exams, right?
Thank you for everything, Professor.
You're
Very much
welcome.
appreciated.
Oh, good.